So I have the privilege of speaking about thermodynamics. Now that may seem like a kind of obscure topic. It's certainly a narrower topic than a typical creation presentation would do. But I think there's a lot of richness here for us to gain from. A lot of information, a lot of different ways we can glorify our Creator through the study. I will first ask the question, is thermodynamics a singular word or a plural word, in case the grammar on that opening slide bothers anybody? I'm not really sure about that, so we went with singular. Thermodynamics is itself a specific topic. It's only one topic of many within the world that we could look at. Now, the Bible tells us, as Chris quoted from, that the heavens declare the glory of God. Now, we should be familiar with that verse, of course, I hope. The Bible tells us that by examining the heavens, we can therefore perceive at least some of God's glory through this study. Now, the Bible doesn't speak specifically of other sciences that we today distinguish as separate fields of study, but I think the same thing would apply. We can glorify God through all areas of science, through all topics within it. Within biology, we can glorify God as an engineer. We see molecular machines made of proteins doing various tasks. We see industrial engineering in the way a cell operates. We see all these wonderful things that we are only now even beginning to be able to understand because of modern technology. We see a lot of the same principles at work in biological systems. Other sciences as well. One of my favorites is ornithology. I mean, we could do a series of talks just on birds. God as an artist, creating iridescence in their feathers. God as a designer. God as an aerodynamics engineer in the ability for these things to fly and the specific design principles within their anatomy that allows them to do that. We could talk about paleontology and the study of the ancient world and all these amazing creatures that God made, many of which aren't here anymore, but nevertheless displaying His creativity. We could talk about geology, appreciating God and His interaction with humanity throughout history. And of course, evidence for a global flood and evidence for His holiness through that. So all of these various sciences, we can glorify God in a different way, usually in multiple ways as we study them. But what about physics? Is it possible to glorify God through the study of physics? Well, my argument tonight is that the answer is yes, that thermodynamics, especially some of the most basic principles within physics, allows us to appreciate a lot of God's glory as the Creator. So what is thermodynamics? Well, thermo means heat, and dynamics means change or motion. So strictly speaking, thermodynamics means the study of the change or motion of heat, the transfer of heat. And there's several laws of thermodynamics. I'm going to limit myself tonight to the discussion of two of them. I'll name them here, and then we'll discuss them in more depth here in a few minutes. The first law of thermodynamics says that matter and energy cannot be created or destroyed. And we'll see here shortly why that's important. The second law of thermodynamics says that entropy in a closed system will always increase. And you might have heard of that. If you don't understand what that means, that's fine, because we're going to take a good look at that here shortly. In creation circles, you will sometimes hear a discussion of the second law of thermodynamics, and specifically, we'll sometimes hear it applied to the fall of man. When Adam rebelled against God and sinned, the creation was then cursed. And a lot of people have said that perhaps this is the source of the second law of thermodynamics. And they will point to this law as the reason for things decaying and death and other consequences. And is it possible then that we can see that the second law began as a result of Adam's sin? We're going to talk about that. I think the answer to that is no. In fact, I think this is one of many misconceptions about thermodynamics from both sides of the origins debate. When we correctly look at thermodynamics, there's a lot of interesting implications for origins. For example, thermodynamics, when applied to the solar system, would indicate that the objects within the solar system are young and not billions of years old. It shows that life requires an intelligent designer. It shows that any model of origins that doesn't include a creator is self-refuting. It disproves itself. And overall, it confirms that a supernatural creator is responsible for the existence of the universe. So here's what we'll be doing tonight in this session. First, I'm going to list a few misconceptions associated with these two laws that we'll be discussing. Then we'll talk about how the first and second laws of thermodynamics work, and this was discovered back in the 1800s. We'll then apply that information to origins, because there's multiple implications for origins through these laws. We'll then use that understanding of those two laws and how they operate to correct and clear up the misconceptions that we start with. Then we'll go a little further. Having discussed how the laws of thermodynamics work, we'll then discuss why they work, something which wasn't discovered until later, into the early 1900s actually. And understanding why they work the way they do then has additional implications for origins, some of which are, I think, really neat. So that's our outline for this evening, and we'll start at the beginning, listing a few misconceptions about the second law and the first law. The second law says that entropy in a closed system will always increase, and a lot of us have heard that. But what is entropy? A lot of us aren't sure about that. You will sometimes hear it said that entropy represents disorder and disorganization. For example, this garage looks rather disordered and disorganized. Therefore, it's an example of entropy increasing. Or is it? As this cartoon says, I blame entropy for the messy state of my bedroom. Is that a valid scientific argument? Probably not a very effective argument with your mother, regardless of whether it's correct or not. But actually, it's not correct. Disorder or disorganization is not a quantifiable or a measurable value. In this garage, you could measure the atmospheric pressure, you can measure the temperature, you can measure the volume, you can measure a lot of things. How would you measure the disorder? What metric would you use for that? What kind of number would you come up with? I mean, there's no real number, right? It's a very subjective thing. So disorder and disorganization is not the same as entropy increasing. Entropy actually is a physical quantity. But even in the creation movement, there's a lot of confusion about this, and so let's talk about some of this confusion here now. Drs. Whitcomb and Morris, brilliant scientist and theologian, pioneers of the modern creation movement, but this is one of the issues, unfortunately, that they didn't get quite right. They said creation, or what biologists imply by evolution, actually has been accomplished by means of creative processes, which are now replaced by the deteriorative processes implicit in the second law. So again, they're saying the second law is a process of deterioration. The latter are probably a part of the curse placed upon the earth as a result of the entrance of sin in Genesis 3, the bondage of decay to which it has been subjected by God for the present age. So you see, they're saying the second law is responsible for decay and deterioration that we see in the world around us, and that this all started as a result of the curse from Adam's sin. This is actually an incorrect argument, as we'll be discussing later. Another incorrect argument that you'll sometimes hear from our side is people say evolution is impossible because it's a decrease in entropy, because molecules to man evolution requires an increase in complexity and order, and if you think that's a reversal of entropy increasing, then you would say evolution is impossible for that reason. But this is a bad argument because entropy is not a direct measure of disorder and disorganization increasing. Now, don't misunderstand me. I'm not saying molecules to man evolution happened or that it's even possible, because it's not. There's multiple reasons why it's not possible, but this particular argument is not among them. This is a bad argument, and so we shouldn't use it. Dr. Dwayne Gish used to use this kind of argument. He once said, this fundamental law of science, talking about the second law of thermodynamics, tells us that an isolated or closed system will never increase in order and complexity. It will never become more highly organized. Again, this is not a correct argument, and this actually had a bad consequence. There was apparently a debate that he participated in. He was famous for participating in lots of debates during his day, if you didn't know that. And his opponent in one of these debates actually used this argument against him. He held up a bottle of salad dressing of oil and vinegar and shook it up so that it was all mixed, and then held it up, and before the audience's eyes, it separated itself out into oil and vinegar. And Dr. Gish's opponent said, well, look, spontaneously, this is an increase in order. It is getting itself more organized before your very eyes, thus disproving what the creationists said. So again, Dr. Gish's argument was incorrect, and that gave the other side something to use against him. You'll sometimes hear crystal formation suggested as an example of spontaneous order increasing, and therefore a debunking of creationist arguments. Some evolutionists have even gone so far to say that babies disprove this argument. As this anti-creationist said, can a few cells floating around in a warm liquid turn into something complex? Clearly, material can acquire complex form. Speaking of the growth of cells into a baby, any claim that some law forbids it is a false claim. So again, when creationists use false claims, the evolutionists are more than happy to use that against us and disprove those claims. Now, they aren't actually disproving correct creation arguments, but this is among the reasons why we shouldn't use incorrect arguments. We shouldn't use incorrect arguments because that's a bad practice anyway, but especially in a debate situation, we don't want to use the other side weapons to use against us, right? We have plenty of good weapons that are not refutable like these are. So we're going to revisit these arguments later once we have a better handle on what exactly the laws of thermodynamics are, and that will illustrate why those are bad arguments. Then we'll talk about some good ones that thermodynamics does give us. So, how do the first and second laws of thermodynamics work? Well, thermodynamics as a science actually goes back to coal mining. Before the Industrial Revolution, in the UK, large deposits of coal were discovered, and people began to mine them and use it for industry. And a very popular steam engine was manufactured in the UK at that time. It was a very inefficient steam engine. It only successfully used about 0.5% of the energy of the coal that was burned to fuel it. But there was such an abundant supply of cheap coal at the time that it still set off the Industrial Revolution, abundant cheap energy as a result of this natural resource. So in the UK, the economy really boomed as a result of this because all these steam engines were built, powering factories, and manufacturing really took off. Now across the water, over in continental Europe, other countries didn't have this blessing of abundance of coal, and they were, however, jealous of English manufacturing, especially in textiles, and they wanted to get some of this commercial gain for themselves. So they began an intense study of how to make steam engines more efficient. They had some coal, but it wasn't as cheap as it was in the UK, so they needed a way to get more energy from a smaller amount of coal, and thus the science of thermodynamics was born. Scientists began to seriously ask questions about how do steam engines work anyway? Why do they work? How can they be made to work more efficiently? Well, this raised more basic questions. These things are powered by heat that we get from burning the coal. What is heat? For a time, scientists thought heat was a type of fluid because it seemed to have some of those properties. Today, the understanding is rather different. Today, we have the kinetic theory of heat, by which heating causes a material's atoms to vibrate more. The hotter it is, the more vibration is going on in the substance. And this also explains how heat can transfer. If you have two chunks of material, one of which is vibrating more than the other, we'll put them in thermal contact so that heat can transfer, and some of the vibrational energy will transfer over to the less energetic one until they are both vibrating the same. Well, this has an implication. In order to transfer heat, to transfer thermal energy from one chunk of material to another, there has to be a difference in temperature. There has to be more vibrating going on over here than there is here. If you have a glass of ice water, for example, you're putting ice in it to make the water cold, right? Because there's a difference in temperature between the ice and the water. Therefore, the heat transfers from the water into the ice. It wouldn't do you any good to put in more water at the same temperature, but that wouldn't accomplish anything, obviously. So this is common sense, right? You need a difference in temperature to transfer heat. Well, there's some implications to that. One of them is that small bodies cool off faster than large bodies do. And I'll explain why this is important in a minute. First, I'm going to explain why. So imagine we have these two balls here, and imagine the material within it. The red represents the heat of the material. And let's assume that these objects are evenly heated throughout. Now, I just said a moment ago, to transfer heat, you need a difference in temperature. You need to be in thermal contact between something that's hotter and something that's cooler. For the large body, only the layer of material on its outside is in contact, thermal contact, with the environment, right? All the stuff inside the ball is surrounded by other stuff that's the same temperature, so heat isn't going to move. The only way to move heat out of this ball is right on the surface. But imagine the smaller body now. Now that smaller circle is actually the same thickness as the larger one. It may seem a little bigger because of an optical illusion here, but it's actually the same. Notice how the small body has a much higher percentage of it in thermal contact with the environment. That means the small body can cool off a lot quicker because a lot more of it is in contact with a cooler surrounding. Okay, so why did I bother talking about that? Because it has implications for origins. If small bodies cool off faster than large bodies, let's apply that same logic to the solar system. There's a lot of small bodies within our solar system that therefore would cool off fairly quickly. Now, something like Jupiter can retain its heat for a long time because it's a very large body, but something like our moon is very small, and thus, as we just saw, will cool off very quickly. So if the moon were billions of years old, as it turns out, it should have cooled off billions of years ago from its formation. So it wouldn't be geologically active anymore because it wouldn't be hot inside anymore. I actually said that backwards. It wouldn't be hot inside anymore, therefore it wouldn't be geologically active today, if it were actually that old. Turns out, though, we're discovering the moon is geologically active, which implies it is still warm inside. We're finding gas venting out of volcanic vents. Recent discoveries show that some of the faults on the moon's surface are active. There are measurable moonquakes going on, apparent tectonic activity, which means the moon is geologically active, which implies it's still hot inside, which therefore implies it hasn't had time to cool off. As this article said, the whole idea that a 4.6 billion year old rocky body like the moon has managed to stay hot enough in the interior and produce this network of faults just flies in the face of conventional wisdom. We're also finding fresh volcanic deposits on the moon. Volcanic activity in a small body that's had billions of years to cool off. As this quote said, this finding is the kind of science that is literally going to make geologists rewrite the textbooks about the moon. So you see how an argument that's coming out of thermodynamics, when applied to the bodies in the solar system, is calling into question the long ages that these bodies are supposed to have. Elsewhere in the solar system, we have Io, one of the moons of Jupiter. Tiny little moon, only about 1.5% of the mass of the Earth, but the most volcanically active body in the solar system, shooting material 180 miles into space. At any given time when we've had spacecraft there, there's usually several volcanoes going off at any given time. Extremely volcanically active body. Well, this requires a lot of energy. But a tiny little body should have cooled off from its formation billions of years ago, if it were actually formed billions of years ago. Now, if you look this up, you'll be told that Io is producing this activity as a result of tidal flexing, where it's caught in a gravitational tug-of-war. There's Jupiter on one side and other moons on the other that's squeezing and flexing Io. That's true, it is occurring, but that accounts for only the small amount of the energy required to explain this geological activity. The better explanation is that it's still cooling off from its recent creation. One of the moons of Saturn, Enceladus, has a similar but different interesting thing going on. You probably can't see very well in the lighting in here, but there's a little smudge below the moon here. Those are the rings of Saturn going across the photo. The spacecraft was almost edge on to the rings at the time. Enceladus, it turns out, has fountains, geysers of water and ice shooting out of its south pole at something like 2,000 miles an hour. Extreme geological activity going on here. In fact, some of its neighboring moons are whiter than they otherwise would be because this moon is spray painting them with ice and snow. Well, where's the energy coming from to do this? Well, again, you'll be told that it's this tidal flexing, this gravitational tug-of-war is squeezing it. That only accounts for a couple of percent of what's necessary to explain this. And furthermore, the pattern of energy distribution in the moon is different than what it would be if that were the explanation. So tidal energy can't explain this. If it were billions of years old, it wouldn't have the energy to do this anymore. The better explanation is that this moon is young, and thus still cooling off from its formation thousands of years ago rather than billions. Another discovery is Pluto. We could spend 20 minutes just on Pluto alone. Lots of fun stuff was found on Pluto with the New Horizons spacecraft. But one of the major discoveries was that large sections of Pluto's surface have been resurfaced. They're young and fresh. How do we know they're young? Because they're smooth and craterless. No craters tells us there hasn't been enough time for anything to hit Pluto since this resurfacing occurred. Well, what would resurface this world? Well, apparently there's volcanic activity going on there, a little bit different than Earth's volcanic activity because the temperature is so different. But nevertheless, cryovolcanoes, as they're known, are flooding the surface with material and smoothing it all out. Now, you'll be told that this is still millions of years old, but as some scientists admitted, it could be only a week old. Maybe this all happened a few days before the spacecraft got there. It looks that young and fresh. So here's a little world on the far edge of the solar system, no source of apparent external energy to have all this geological activity. Unlike the previous two examples I gave you, there's no tidal flexing going on with Pluto, nor is there a significant source of radiometric heat inside. The only reasonable explanation is primordial heat, heat left over from Pluto's formation. But it's a tiny little body, can't retain heat for very long, as we've seen from thermodynamics. So it should have cooled off billions of years ago, but it didn't. That implies it's very young. As these scientists admitted, finding that Pluto is geologically active after 4.5 billion years, there's not big enough typeface to write that in. It's unbelievable. So we see then, thermodynamic arguments can actually be applied in some interesting ways. Let's dig a little deeper into some of these principles and see what else we can glean. The first law of thermodynamics says heat energy can't be created or destroyed. I have heat in brackets because that was the original understanding and has now been broadened to a broader principle. Now, this has long been understood. I mean, it's common sense. If you want your locomotive to move, it's not going to move until you shovel coal in the boiler and ignite it, right? You don't get energy from nothing. You have to get it from some source, in this case, coal. Well, subsequent advances in science have now broadened this principle to a much bigger understanding than merely coal and steam engines. Physics now has the idea of matter and energy equivalence. You've probably heard the famous equation E equals mc squared. Matter and energy are now understood to be two different sides of the same coin, so to speak. You can convert them one to the other, and I'll talk about that in a moment. The equation tells us E is energy, m is mass, the amount of stuff you have, and c is the speed of light, which is a very large number, and even larger in this equation because it's squared. So this tells us that a little bit of stuff, physical stuff, contains a lot of energy. And the first law of thermodynamics has now been broadened into what's called the conservation of matter and energy. Not only is it impossible to create heat energy from nothing, it's impossible to create matter or any kind of energy from nothing, because the total amount of matter and energy in the entire universe is conserved. It always stays the same. Now, that's a total number, so you can change the relative amounts of one or the other as long as the other one goes up or down to compensate. So, for example, we can convert matter into energy, and the most efficient way we know how to do that is a nuclear explosion. A little bit of stuff turns into a lot of energy. But you didn't get the energy from nothing, right? Because that would violate this fundamental law of physics. You had to get it from the physical stuff. So we can convert matter to energy. We can go the other direction and convert energy into matter. We do that in particle accelerators. Little chunks of matter get zipping around at close to the speed of light and smash together. Now, these explosions, I should say these collisions rather, can be rather spectacular. More stuff comes out of the collisions than went in. I don't just mean the number of particles, I mean the amount of physical matter. But are we creating matter from nothing? I mean, there's more at the end of the experiment than there was at the beginning. Well, no, we're not. We're converting the kinetic energy, the energy of motion that we're sending these things around the accelerator, we're converting that energy into matter. So my point is we can convert matter to energy, we can convert energy to matter, but you never get either one from nothing, because that violates this law of physics. And we have everyday experience with this law. It applies to our everyday lives. I mean, think about it. Why do we need to eat food every day? Regardless of how difficult that process might sometimes be. Because you need energy for your food, for your body to operate, can't make it from nothing, can't get it from nothing, because that would violate this principle in physics. So we have to get it from the chemical energy stored in the food. Of course, you have to get it in your mouth first, but that's a different story. Why do you get a bill from the power company every month? Because your appliances need energy to operate, but can't get it from nothing, because that violates physics. Have to get it from an external source, which also can't get it from nothing, because that would violate physics. It has to get it by burning coal, or capturing gravitational potential energy from flowing water, or perhaps solar energy from the sun, which also can't get it from nothing. The sun produces energy by burning hydrogen, and so on. So all through physics, we see this fundamental principle. In fact, you couldn't be watching this presentation tonight because some of the principles of circuit design are based on this. I mean, if you have one of these things in your pocket and it works, then this principle in physics is true. Because one of the first things an electrical engineer learns is some principle called Kirchhoff's laws, which applies this law of thermodynamics to circuit design. And indeed, different areas of physics have this same principle applied in different ways. As one of my textbooks says, conservation laws are the guiding principles of physics. These are absolute conservation laws. They are always obeyed. So I'm emphasizing the point, always obeyed, fundamental part of physics, fundamental laws of physics. So what implications does this have for origins? Well, if you can't create anything from nothing, then that applies to the question of where the universe came from. If you're going to say that there was nothing, and then suddenly there was the universe, well, that's a largest possible violation of this principle in physics, right? I mean, we can't create even 1 gram of matter from nothing in the laboratory. Yet we're going to say all the planets, stars, and galaxies in the entire universe, or at least their predecessors, the matter and energy responsible for that all leapt into existence from nothing? No, physics tells us that everything could not have come from nothing. So the first law of thermodynamics disproves an entire category of cosmogonies. Cosmogony means history of the universe. So the Big Bang is an example of a cosmogony where it says something came from nothing. So the first law of thermodynamics says that if you're going to have this in your model, that's not allowed by physics. Therefore, your model violates the laws of physics. So that's what the first law of thermodynamics tells us about origins. What about the second law? The second law says entropy in a closed system will always increase. This has implications for origins too, but first we have to discuss what exactly this law means. You'll see different definitions for the second law. Some of them are imprecise, but the more precise ones are kind of hard to understand. Like this one says, entropy change is the measure of how more widely a specific quantity of molecular energy is dispersed in a process. So what does that mean? Well, one of the key ideas here is energy dispersal. A physical process requires energy to be dispersed. For example, if you burn firewood, you start out with a physical thing, the chunk of firewood, that's solid chemical energy in a sense. You now set it on fire. What happens? That mass, that physical stuff, turns into heat, light, kinetic energy, the motion of the rising air, particles in the smoke, and some other things. The thing I'm focusing on here is the dispersion. You started out with energy that you could hold in your hand. What do you have after it's all gone? The energy didn't disappear. It turned into all those other things. But is the light that shone from the fire available for you to use in some other way? No, it's gone. The heat, can you do anything with it? No, it went into the atmosphere and then will radiate out into space eventually. So the energy didn't disappear, it just dispersed and therefore became unavailable for you to use subsequently. So what's the implication for origins? Well, the implication, this one's very important. One implication is that hot things cool off. Well, that's a brilliant statement, Spike. We're so glad we came to your talk tonight. No, this is actually a very profound statement if you think about it. Think about something hot, like a cup of coffee. Thermodynamics tells us we can use that as a crude form of clock. What do I mean by that? Well, if you walk into a room and there's a hot cup of coffee sitting there, how long has it been there? A long time or a short time? Short time, right? Because had it been there a long time, it would have cooled off long ago. You know for sure it hasn't been there infinitely long, because then it would have cooled off eternally long ago, right? We can use the same reasoning and apply it to the universe. Is there anything in the universe that hasn't cooled off yet? Stars. Lots of them. So if the universe were eternally old, we know that stars cool off because they consume their fuel, of which there's a finite supply. Eventually, all stars will burn out. That means if the universe had been here forever, all the stars would have burned out forever ago. But they're still there. That tells us the universe hasn't been here forever. See the logic there? The universe cannot be eternally old. Now, some people will say, wait a minute, new stars can form. There's actually problems with that statement, but setting those aside, there's still a finite amount of energy available for that. So that too would have been consumed forever ago if the universe had been here forever. So just the fact that we still see stars, applying this reasoning from thermodynamics, tells us that the universe cannot be eternally old. It hasn't been here forever. And if it hasn't been here forever, that means it had to have a, what? Beginning. You will sometimes hear Christians say that we should embrace the Big Bang model because it shows how the universe had a beginning, and that's consistent with Genesis. Actually, the Big Bang model is not consistent with Genesis, but my point right now is we don't need the Big Bang model to show that the universe had a beginning. If you want to prove the universe had a beginning, walk outside and look up. Do you see a sun during the day? Do you see stars at night? If so, this shows that the universe had a beginning. So we've talked about how the first and second laws work, and again, this goes back to the 1800s, and we've talked about their implications for origins from those. Now we're a little better equipped at how these laws work, and so now we can go back to some of those misconceptions that we talked about earlier and clear them up. So when people say evolution is impossible because it's a decrease in entropy, actually no. Remember, entropy is tied into the dispersal of energy and some other things that we'll talk about shortly. The Earth is not a closed system, so in theory, you could locally have entropy run backwards and decrease as long as the entire universe's entropy increases. And if that, I don't want to spend too much time on that point. I hope that made sense the way I worded it. But the point is, you can't apply entropy only to the Earth and thereby disprove evolution using thermodynamics. This is not a valid argument. What about the idea of the separation of oil and vinegar? Well, actually, it turns out that the separated state is the lower energy state, and that's actually entropy increasing. So again, a simplistic association between entropy and order is not justified because there's more going on under the hood here. Same thing with crystal formation. As crystals form, entropy actually increases. And that has to do with molecular structure and the way that they're designed to grow and when put in these circumstances. Point is, when an evolutionist says crystal growth disproves creationist arguments about entropy, no, because actually entropy is increasing in those circumstances. Same thing with growth of a baby. The overall entropy of the universe increases when a baby grows, not decreasing. What about something a little more relevant to some of our arguments in the fall of man being the source of the second law? When you really think about this, I'm going to argue that this is not a valid claim. For one thing, digestion needs the second law of thermodynamics to work. Were Adam and Eve able to digest food before the fall? I mean, I think so. God told them to eat. That implies they were able to handle the food that they consumed. Walking, it turns out, is also an increase in entropy because it requires friction between your feet and the ground or the floor. If it were a frictionless surface, I mean, imagine standing on ice, but that was perfectly slippery, you wouldn't be able to stand up, right? There needs to be a little bit of friction. Well, friction dissipates heat, which means entropy is increasing. So if Adam and Eve could walk in the garden, and I think the Bible's clear that they could because it says they did, then the second law was operating at that time, even before the fall. So what changed at the fall? What changed when the curse was imposed on creation if it wasn't the second law being imposed on the world. Personally, I think it was the removal of divine sustenance. We have other examples in the Bible of where the Lord suspended processes like decay in order to accomplish his purposes, like the Israelites being in the wilderness for 40 years and their sandals didn't wear out. Now, they were able to walk in the wilderness, which means there was friction between the sandals and the ground, which means entropy was still increasing. Nevertheless, the normal consequence of the sandals being ground down and worn did not happen because the Lord sustained them miraculously. So I think the second law was in operation in the garden before the fall, but the Lord was suspending its harmful effects like decay and death and so on. The Bible doesn't tell us this specifically, but I'm just giving you my conclusion from that. You can accept it or reject it as you will. What other arguments can we get from thermodynamics that are actually valid rather than based on misconceptions? Well, you can apply thermodynamic arguments to the origin of life. There's many, many problems trying to get life from non-living chemicals, but thermodynamics actually operates against that idea as well. Among other things, there's a problem of chirality, where amino acids can come in a couple of different forms. And it turns out if you make amino acids just from random processes, you get an equal mixture of both forms. In life, however, amino acids are all in the L form. All the proteins in your body have amino acids in L form. That tells us that it did not originate from some random pond of goo billions of years ago, because a random pond of goo will, even if you can make amino acids in it, which is not all that easy, will have an equal mixture of left and right. And by the way, even if you filter out all the left and somehow set them aside, over enough time, again due to thermodynamics, some of those will change into the other form. So life, just in its very structure biochemically, using thermodynamic arguments, can be shown to not have happened by itself. DNA decay. DNA turns out to be a very delicate molecule. Left to its own devices, it will break down fairly quickly, again as a result of increasing entropy from thermodynamics. And people have even studied how quickly this would happen, and this is interesting because this study found that when you take samples of tissue, even when you freeze it and totally seal it off from oxygen, the DNA will still decay. It's slower than if it were sitting out in the counter somewhere, but it'll still happen even under those conditions. And even under those conditions, as these scientists found, they found that no intact base pair bonds would remain in the strand of DNA after 6.8 million years. So, of course, they didn't measure it that long, but they measured it in the lab for a while, extending that out. After just 6 million years, then, there should 6.8 million years specifically, there should be no intact DNA bonds anymore. Presumably even a shorter time than that, actually, because a fossil off in the wilderness somewhere is obviously not frozen, and nor is it sealed off from oxygen, water, and things like that. But despite all of this, there's evidence for DNA in dinosaur fossils. Now, the youngest dinosaur fossil is supposed to be 65 million years old, almost 10 times as long as the time after which all DNA base pairs will be gone, or broken, I should say. Nevertheless, there's DNA in some of these tissues, which implies, therefore, these things are not actually millions of years old. And at other talks here, if you've been attending for a while, you've no doubt heard about dinosaur soft tissue, collagen, bone proteins, and other examples of things within dinosaur fossils that should not be there at all after millions of years. But they are there anyway, which implies these fossils are not actually millions of years old. What about other applications of thermodynamics? One of my favorites is what I call the secular dilemma. It's based on a simple question, just 6 words. Did the universe have a beginning? How many possible answers are there to this question? Just 2, right? Yes. Either yes, there was a beginning, or no, there was not a beginning, in which case the universe must be eternal. Why do I call this secular dilemma? Well, secular means we're not thinking in terms of creation. Let me reword that. It's a dilemma for people who do not accept creation. And a dilemma is a choice between equally bad alternatives. So this question, if you're a secular thinker and I'm trying to explain the universe without a creator, you only have two choices to answer this question. Both of them are bad for you. What do I mean by that? Well, let's say you want the answer to be yes, there was a beginning to the universe. And again, we're thinking like secular cosmologists here, trying to explain the universe without a creator. Well, if you say there was a beginning, the universe had a beginning, and the universe is everything, well, if everything had a beginning, then what was there before that beginning? Had to be nothing. Because if there was something before the beginning, then whatever began was not everything. It was only part of everything. So, if you're a secular cosmologist and you want to believe that everything had a beginning, then before the beginning there had to be nothing. And again, some versions of the Big Bang model have a beginning from nothing. So I actually have a graphic here showing what the universe looked like before the Big Bang happened. It's nothing. Of course, that's only an artist's conception. But serious question, can nothing make everything? If there was no external creator and everything came to be, then it made itself? That doesn't make sense. Maybe the nothing made the everything. That's your other option. Well, that doesn't make sense either because nothing can create nothing. Nothing can do nothing. From nothing comes nothing. Dr. Phil Fernandez, who's spoken at, locally here quite a few times, mentioned something like this a while back. I like the way he phrased it. He said, "You can't tell me nothing made everything because I know too much about nothing." And of course, this all ties back into the first law of thermodynamics, doesn't it? The conservation of mass energy. If the combined amount of matter and energy in the universe never changes, you can only change the relative amounts of each one, but can't get either one from nothing, well, that tells us the universe couldn't have come from nothing either, which discredits these secular cosmologies. Now, if you've studied these type of issues, you'll be aware that some secular cosmologists claim that something can come from nothing, like this best-selling book from Dr. Lawrence Krauss said. I won't spend time on this here. If you're curious about it, ask me during Q&A, and we'll revisit this. I'll just say for now that his claims are not correct. Because the first law of thermodynamics is clear. You can't get anything from nothing. That means that there could not have been a beginning to the universe according to secular cosmology. So if you're trying to make a secular cosmology, the yes answer to this question is not available to you, so the answer must be no, right? That's your only other option. Well, let's talk about that. The universe must, if the universe didn't have a beginning, there must always have been something. So the universe in one form or another must be eternal. But we talked about this already too, didn't we? Second law of thermodynamics says the universe can't be eternal because there are still hot things within it. If the universe were eternally old, heat energy would have spread out and distributed itself perfectly evenly, subject to minor variation, but more or less evenly throughout the universe. But is that the universe that we see? No, we see vast expanses of very cold space punctuated by very hot objects that haven't distributed their heat yet. So this tells us the universe is not eternally old, like we talked about before. Now, sometimes you'll hear people say, wait a minute, how about the idea that the universe is eternally oscillating? There's a big bang, it spreads out and then collapses into a big crunch, and then rebounds, bang, crunch, bang, crunch, bang, crunch. You will hear this seriously suggested sometimes, but thermodynamics doesn't allow that either because thermodynamics says this process is still going to have increasing entropy throughout, and eventually it's going to stop. I mean, if I held a basketball here and dropped it, it'll bounce a few times maybe, if this surface were hard enough, but is it going to bounce forever? No, because it's losing usable energy every time it hits and flexes and heats up and so on. So just like a basketball can't bounce forever, so a universe can't do that forever either. So now we see, hopefully, why this is a dilemma. Because if you're trying to create a cosmology without a creator, you have to answer the question, did the universe have a beginning? We already saw the answer can't be yes, because of the first law of thermodynamics. And now we see the answer also can't be no, because of the second law of thermodynamics. And those are the only two options that the secular cosmologist has. Thus a dilemma. He has two choices, and they're both bad, because neither one can be correct. Now, as Christians, we have a third option, that there's a supernatural creator outside of the universe. Yes, the universe had a beginning. We know that because of the second law, shows us it's not eternally old. But a supernatural creator outside of the laws of physics brought the universe into being. That's the only explanation for the universe that doesn't violate the laws of physics. Because if you think about it, there's really only three possibilities for the universe existing. Number one, it was formed by a creator. Number two, it formed without a creator. Number three, it never formed at all because it's always existed. Something has always existed. We saw that option two, that it formed without a creator, is not a good option because of the first law of thermodynamics. And then we saw that the last option, that something has always existed, is not allowed by the second law of thermodynamics. The only viable option that's consistent with the laws of thermodynamics is that the universe is here because of a supernatural creator outside of the universe. So thermodynamics says that atheistic cosmogonies, atheistic cosmological models, are not allowed because they're going to violate physics in one way or the other. And if it's not clear, this is more than just the Big Bang model. Any atheistic cosmology has to wrestle with that dilemma and is going to violate physics one way or the other. And this is a great conversation starter, by the way. If you're talking to people about the big questions in life, you can ask them, hey, what do you think about this? Did the universe have a beginning or not? Let people think about the implications of that, how many possible answers there are, and then whichever answer they pick, you can share with them how physics doesn't allow that answer. Because physics ultimately shows that there has to be a creator. And I view this as not merely a scientific issue. To me, this is also evidence of God's grace. I mean, think about this. The Lord could have made the universe look like the product of natural processes. It would be within his right to do that, right? And as long as he told us, pay no attention to the atheists, trust me, I made this, he would be within his right to do that, to ask that of us. But in our weakness, how many of us would have strong enough faith to be able to do that? Some, perhaps not most, certainly not all the people who believe in it today. God knew our weakness, and again, the Bible doesn't say this specifically, but I view this as one of the many manifestations of grace. God placed us in a universe that looks created. The laws that it operates according to also show us a creator was necessary to explain its existence. And I think that's really cool. Very thankful for that. So, moving back to our outline, we talked about misconceptions, and then we talked about some valid applications of thermodynamics. And those were all based on how the laws, the two laws that we're discussing, how they work. Let's talk about why they work. And this took a while for scientists to figure out, because this has additional implications for origins. So why does entropy increase anyway? Why is this such a consistent pattern of behavior for the universe? Well, this goes back to the work of Ludwig Boltzmann, who passed away in the early 20th century. And he was the first one to really provide a solid mathematical foundation for why entropy increases. And without getting into all the math, I want to conceptualize this a little bit. Let's think about the air, and this is going to seem strange for a bit, but bear with me. You'll see how this is relevant. Think about the air in this room. We're all breathing air right now, right? There's enough pressure here for us to be able to breathe. Imagine that this room was a vacuum. No air inside of it. No gas. Now let's imagine the room is divided into 6 zones. Let's in our minds, divide the room in half this way, and then we'll divide each half in 3 divisions so that there's 6 zones within the room. Now let's think about individual molecules of gas, oxygen, carbon dioxide, or whatever. If there's 6 zones within this room, you could represent the location of a single molecule, which just moves around at random. It's going to wind up in a region at random, so you could actually think of it like rolling a die. The die will show a number 1 through 6, and that tells you where the molecule of air or oxygen or whatever is at that moment. Okay, so if we have each die represents a molecule of gas, and the number on the die tells us where in the room the molecule is located. Okay, again, this is going to seem strange, but bear with me. Let's say there's 1 molecule of oxygen zipping around in here. If there's 6 possibilities for where it could be, and it's moving around at random, then there's an even chance it could be in any 6 of those regions, right? Seems straightforward. Just like rolling a die, you're going to get a number 1 through 6. So with just 1 molecule of oxygen, in this case, it could be anywhere with the same odds of being in any given place. What if there's 2 molecules of oxygen in the room? Well, now, representing this by dice again, how many possible combinations of dice have all of the molecules in the same region? Only these 6. I hope you're staying with the analogy here. If the dice show us where the molecules are at any given moment, there's all these various combinations of 2 dice that you can get, right? Of all those combinations, only 6 of them mean that both molecules are in the same place. So with just 2 molecules, the odds of them being in the same place in the room are 6 out of 36, which is 1 out of 6. The numbers change drastically the more molecules you have. If there's only 3 molecules of oxygen in the room, their odds of all being in the same place are 1 out of 36. 4 is 1 out of 216. 5, 1 out of 1,296. You see how that number is going up. The more molecules there are, the greater the odds against them all being in the same place. And how many billions of molecules of gas are in this room right now? With so many molecules, the odds of them all being concentrated at one spot are infinitely small. Almost infinitely small, I should say. That's why it's evenly distributed, and that's why it's possible for us to breathe in here right now. I mean, were you worried that all the air was going to rush up to that corner and leave you in a vacuum asphyxiating? Of course not. That doesn't happen. Why? Because they're all moving around, and even though it's at random, they're never all going to wind up in one spot because of how the numbers work. I hope you're all still with me. This reasoning shows us why the second law of thermodynamics works, why entropy always increases. It's why hot things cool off. Instead of molecules, think about calories. If I have a hot cup of coffee, there's a higher concentration of calories in the cup than the room. But as heat is being exchanged, the number of arrangements of calories in the room is far greater for even distribution than concentration versus colder. Everyone see that? If you put a hot cup of coffee here, you're not worried that it's going to suck all the heat out of the room and boil over while the rest of us freeze. No, it works the other way. Because of that same math, the more molecules or the more calories that you have, the math means it's going to be more evenly distributed, even when you start out with a concentration. This also explains the apparent association with increasing entropy and disorganization. There's a lot of stuff in this garage, right? A lot of different objects. How many possible arrangements are there? Well, thousands at least. Of all the thousands of ways to arrange all the stuff, how many of the arrangements represent an arrangement where everything is in its exact place where it's supposed to be? 1. There's one way to arrange everything where everything is in its proper spot, and thousands of ways to arrange it where at least something is not in its proper spot. That's why if you just move stuff around in the garage without being deliberate about it and introducing an intelligent agent into the process, it's going to move from what we consider order to disorder. It's because of the same mathematics. Okay, by this point you're wondering, what's the point, Spike? Why don't we just wade through that? That was tedious. Well, the point is, we can mathematically quantify the probability of different arrangements of matter and energy. it is much less probable that a cup of coffee is going to stay hot over long periods of time, much more probable that the heat is going to disperse itself because of entropy. I should say overwhelmingly more probable. It's not just a small thing, because this is how the world works. And there's an association, therefore, between entropy and probability. A system with low entropy is less probable. Over time, entropy increases and goes higher because it's moving toward a more probable configuration. Just like the garage, you start out with the garage perfectly organized, and then you start using stuff. What happens? It evolves into a higher entropy state where things are not where they're supposed to be. Okay, but applying this reasoning to the universe, low entropy arrangement of matter and energy is less probable. High entropy is more probable. Guess which one the universe is? When we measure the entropy of the universe, is it low entropy or high entropy? Turns out it is very low entropy today. The universe is in an extremely improbable configuration of matter and energy. Well, think about this. Entropy increases over time, and it's still very low today. Looking backwards into the past, that means it was even lower. So looking backwards into the past, the universe was less and less probable, even than the improbable state it's in today. So even if something could create itself, which as we already said is impossible, but forget about that for a moment, you'd still have to say the universe sprang into existence in an extremely improbable condition. Even something like the Big Bang has to have the universe look intelligently designed at its very beginning, because it's still very improbable today, which means it was even more improbable in the very beginning, which makes it not look like the outcome of random processes. Here's an illustration I like to use for this. Let's say you have a friend who's trying to explain the bizarre nature of politics in our country or whatever. He said, where did Washington, D.C. even come from anyway? Well, you know, I think I've solved this. I've come up with a model. This is what your friend says to you. I've created a model that shows where Washington, D.C. came from. It sprang into existence from nothing. And you say, cities don't spring into existence from nothing. That violates physics. Well, I think things can pop into existence from nothing because I read a book by Dr. Lawrence Krauss that said it's possible. Okay, well, we'll set that part of it aside for a moment, and let's consider the implications if it did. You're talking about a city that contains hundreds of thousands of people, all of us, or all of which are extremely complex organizations of matter. You're talking about a city that has buildings, intelligently designed systems, road networks, traffic systems, water and wastewater management, and also things like artifacts like the Declaration of Independence, right there in Washington, right, on display. And you point out to your friend, you know, you're saying that everything within the city had to pop into existence from nothing. Are you going to have the Declaration of Independence pop into existence from nothing just at random, complete with all the signatures and all the rest of it? Does that make sense? Well, no. The Declaration is not going to pop into existence from nothing. But even that idea, as silly as it is still much more probable than the entire city containing the Declaration popping into existence. Some of you are probably wondering why you came to this talk tonight. This is pretty weird stuff. Bear with me. So as silly as the idea is that the Declaration of Independence could pop into existence from nothing, it's still much more probable than the entire city that it's contained within doing that. Everyone see that? We can use that same reasoning and apply it to the Big Bang model. The universe, according to the Big Bang, is in such an improbable state, specifically in the very beginning of it, that something else happening is far more probable. What am I referring to here? This is called the Boltzmann brain paradox. It points out that mathematically, if something could come from nothing, which is impossible, like we said, but a lot of secular cosmologists don't want to accept that. Even if something could come from nothing, it's much more likely that it wasn't an entire universe popping into existence at the Big Bang. Instead, only a single brain popped into existence, yours. Here's an article in the New York Times talking about this. It could be the weirdest and most embarrassing prediction in the history of cosmology, if not science itself. If true, it would mean that you yourself are more likely to be some momentary fluctuation in a field of matter and energy out in space than a person with a real past in an orderly star-spangled cosmos. Your world, your memories, and the world you think you see around yourself are illusions. In other words, you popped into existence a few seconds ago from the void. That was what popped into existence from nothing. Now you may think, wait a minute, no, I led a whole life, I had memories going back. No, your brain just happened to pop into existence with the chemicals arranged in such a way that you have all the false memories. And the false perception of being here in this room, hearing this presentation tonight. It's all an illusion. This bizarre picture is the outcome of a recent series of calculations that take some of the bedrock theories and discoveries of modern cosmology to the limit. The basic problem is that it's hard for nature to make a whole universe. Thermodynamics shows us that the Big Bang universe is extremely improbable. It's much easier to make fragments of one, like planets, yourself maybe in a spacesuit, or even in the most absurd and troubling example, a naked brain floating in space. Nature tends to do its easiest from the standpoint of energy and probability, and so these fragments, in particular the brains, would appear far more frequently than real full-fledged universes, or than us, or they might be us. Alan Guth, a cosmologist at the Massachusetts Institute of Technology, who's a rock star in cosmology, by the way, who agrees this overabundance is absurd, pointed out that some calculations result in an infinite number of free-floating brains for every normal brain meaning there was a real universe and Darwinian processes evolved into people, which means the math makes it infinitely unlikely for us to be normal brains. Those are his words. So the odds are 1 out of infinity, according to the Big Bang model, that you're a real person in a real room hearing a real presentation tonight. Because there's an infinite number of, mathematically it's infinitely more likely that you're just a brain floating in the void. So getting back to our analogy, as ridiculous as it was to say the entire universe of Washington, D.C. popped into existence, and it's still ridiculous to say that the Declaration would pop into existence, if something had to come into existence, you'd have to say it was the Declaration, because that's far less ridiculous than the whole city that it's within. This is why I use that analogy. The Big Bang universe is so mathematically unlikely that if something did pop into existence, it's infinitely more likely, mathematically, that it was only your brain. This is called the Boltzmann brain paradox, and just to clarify, this is not saying that you are a brain floating in space, because there is no space, it's just you. Now, by this point in the presentation, you're saying, okay, Spike, we were with you to this point, but you've finally gone too far. I'm not making this stuff up. You can look in the cosmological literature and you will find secular cosmologists wrestling with what their model says about reality. As this author said, a typical observer in the multiverse is a Boltzmann brain. In the eternally inflating vacua, observers are infinitely more likely to be Boltzmann brains than honest folk like ourselves. This author said, the most likely fluctuation consistent with everything you know is simply your brain, complete with quote-unquote memories, fluctuating briefly out of chaos and then immediately equilibrating back again. This is sometimes called the Boltzmann's brain paradox. This paper, Avoiding Boltzmann Brain Domination in Holographic Dark Energy Models. A note on Boltzmann brains. Sinks in the landscape, Boltzmann brains and the cosmological constant problem. This author was hopeful that the Higgs boson could save us from the menace of the Boltzmann brains. But alas, turns out it couldn't. This author was wrestling with Boltzmann brains and the scale factor cutoff measure of the multiverse. Now, for a while, cosmologists thought they solved this problem, but then it turned out that they didn't. And indeed, they wrote about the return of the Boltzmann brains. So I'm making the point here, this is not something I made up. Secular cosmologists wrestle with the fact their models say it's infinitely more likely that the universe itself doesn't exist, that you're just a brain floating in the void, and all of this around you is illusions. That's what the math says. So what does secular cosmology actually predict as a result of all of this? A universe or just a brain? It's just the brain. So secular cosmologists and atheists in particular often think that science gives them a great weapon to use against the Bible, but no. Because this means the Big Bang model says that you're a Boltzmann brain, which means there is no universe, which means the Big Bang never happened. So the Big Bang model says the Big Bang never happened. The Big Bang model disproves itself. So science does not give atheists a great weapon to use against the Bible. The only weapon that science gives them is this one. And this is all the result of those fundamental laws of thermodynamics that we talked about, that we've been talking about. So I hope all of that made sense. I know some of these are pretty weird concepts, but that is actually what the math says. When you take these models to the logical conclusion, you wind up in absurdity. So tonight we've talked about a variety of different ideas. We've talked about some bad arguments that we should avoid, discussed how the fall of man is probably not the source of the second law of thermodynamics because digestion and walking and other things rely on it. I think God miraculously and divinely sustained the creation up until the fall and then removed some of that. So entropy is not merely a matter of organization or complexity increasing like we talked about. It's actually more complicated than that, so we should avoid using these bad arguments and instead focus on good arguments like based on the first law of thermodynamics and the second law, that small bodies cool off faster than large ones, which shows us that many of the bodies in our solar system can't be very old, that life couldn't have formed by itself, that processes like DNA decay indicate that dinosaur tissues and other things aren't that old. And the ultimate absurdity in all of this, when applied to secular models at least, is that thermodynamics shows that secular cosmology predicts that the universe itself isn't real. And I think all this is fun because thermodynamics ultimately began with commercial intent. Scientists were studying thermodynamics to understand how to make more money so they can compete with the British. So what began with the commercial intent ultimately reveals truths about our origins, which I think is kind of fun. And if there's one thing to take away from tonight, I would like it to be this, the secular dilemma. Thermodynamics tells us that even though a secular cosmologist has to say either the universe had a beginning or it didn't, both answers are not allowed by the laws of thermodynamics, and this is a good way to start conversations with people. Get them thinking about the implications of that. Physics guides us towards the recognition that the universe has a creator because indeed thermodynamics confirms creation. That's the end of my prepared material this evening. Chris had my website on an earlier slide, creationastronomy.com. If you like this rather unusual perspective on physics and astronomy, we touched only briefly on astronomy tonight. This entire site is dedicated to that.